So 2.4, right, this is lesson 2.4, and we're going to look at deductive reasoning, both the law of detachment and law of syllogism. So we use a lot of inductive and deductive reasoning every day, every minute as we kind of process information and make conclusions about things. So for our first example, talking about the weather, in Miguel's town, the month of April had the most rain for the past 5 years. He thinks that April will have the most rain this year. So is he using inductive or deductive reasoning? Well, when we talk about inductive, we're looking more at observation. And when we talk about deductive reasoning, we're looking more at facts. So for this example, I would definitely say his conclusion is based on observation. So this is inductive reasoning because he is thinking it's going to rain more because April last year had more rain. So in this next one, Sandra learned that if it's cloudy at night, it will not be as cold in the morning than if there were no clouds at night. So Sandra knows it will be cloudy tonight, so she believes it will not be cold tomorrow morning. So learned that this is a fact, and so hers is using facts. So she is using facts. So this is deductive reasoning that she is using. So to deduct from the facts, that's what we have, inductive and deductive. Now we're going to look at law of detachment. So law of detachment is basically a statement, an if-then statement that's true, and then we state the hypothesis, and then we can conclude the conclusion. Basically, that's how law of detachment works. So this example here, if a car is out of gas, then it will not start. So then they give an example, well, Sarah's car's out of gas. So we can then conclude her car will not start. So again, we always have to have the if-then statement. We have to be given the hypothesis, and then we can conclude the conclusion. And it has to go in that order. So we're going to write either it's valid, it's following that law of detachment, or it's not, and it's invalid. And we have to kind of explain why. Okay, so let's look at our statement here. It says if a figure is a square, then it is a parallelogram. So we have our, and I'm going to kind of label the parts so you can kind of see them, and it'll help you a lot more when we get to our next example. So P and Q. And then they give us, it looks like it's saying the figure is a parallelogram. Well, that's Q. Can we take the conclusion and then conclude the hypothesis, the P? No, we can't go from the conclusion to the hypothesis. So for this one, we would put in valid, just knowing the conclusion doesn't make the hypothesis true. So we can't go from the conclusion to the hypothesis. That's why this is invalid, doesn't follow that law of detachment. So let's take a look at another example on the next page here. So for this one, it looks like if the side lengths of a triangle are 5, 12, and 13, there's our P, then the area of the triangle is 30. So then it's saying the area of the triangle is 30. Well, it's giving us the conclusion, can't make a good cue here, and then it is trying to have the conjecture of our hypothesis. So again, this is invalid because it's doing exactly what it did on that first one. Again, knowing the conclusion doesn't make the hypothesis true. All right, so this next one, if you want to try it on your own, go for it. If the World Series, or in the World Series, if a team wins 4 games, P, the hypothesis, then the team wins the World Series, conclusion Q. So it's saying the Red Sox won 4 games. Oh, there's our hypothesis. It's giving it to us first. Can we conject the conclusion? They won the World Series. Yes. So if it again gives you the P first, then you can have the conjecture of Q. So this is valid. All right. So now we're going to look at one that has a Venn diagram kind of with it. So triangle is equilateral. There's our P. Then it is an acute triangle. There's our Q. So it's giving us the P, and then it's giving us the Q. So it is following it here in the word format. Let's take a look at it kind of in this Venn diagram format. So over here, we have our equilateral. So at any point, no matter where we draw a dot, if we draw it here, if we draw it here, wherever you draw that dot for an equilateral triangle, it will always be inside of the circle for acute triangles. So whether we draw it here, it's still within, because this is within the acute. So that is how we can say valid as well using the Venn diagram. So valid no matter where you draw a dot for an equilateral triangle, it will always be inside the circle for acute triangles. Oh, there we go. All right, now we're going to lastly talk about law of syllogism. Now, law of syllogism has kind of 4 parts. We have, and they kind of color code, which is nice. We have our P, we have a Q, then we take our Q, and then we go to R. Okay, so P to Q, then Q to R. Now, basically, I think of it like a choo-choo train. We're going to just basically take the beginning and the end and put them together to make a valid conclusion. So we kind of cut out that middleman, both of those Q's, and we put the beginning and the end together, and that is what law of syllogism is. Okay, so it has to go in that order. So if he finishes his homework, he'll go out with friends. So this is our P, this is our Q, and then if he goes out with friends, again, that's our Q. Then R, he'll go to the movies. So we're going to take this first part and this last part and put them together, kind of almost ignoring that middle part and saying if he finishes homework, he'll go to the movies. So now we're going to look and see, is that A? Nope. Is that B? Yes, there's B. If he finishes his homework, he'll go to the movies. Okay, so that's what we can say with the P and the R, beginning and end. All right, so this next one, if a figure is a kite, there's our P, then it's an equilateral, then it is equilateral, there's our Q. If it's equilateral, there's our Q, then it is a polygon, there's our R. So we're going to be putting the P and the R together. If it's a kite, then it's a polygon. Yep, there's our P, there's our R, so this is valid. Comma follows law of syllogism. All right, so try that last one on your own if you'd like, before we move on to one final question. And hopefully you saw that this one is invalid. If it's divisible by 2, then it is even. There's our P and our Q. If it is even, Q, then it is an integer. So it should be saying if it's divisible by 2, then it is an integer. So this and this should be switched because we want it to not be R and then P. We want it to be P and then R. So this is invalid. Doesn't follow that law of syllogism. It has to be P then R for our final conjecture. All right, last example, we're going to draw a conclusion from the given statements and then state whether our conclusion is drawn from law of detachment or law of syllogism. If there is no valid conclusion, then we'll write no conclusion and explain. So if it snows more than 5 inches, school will be closed. It snows 7 inches. Okay, so on this last one, so for this one, we have our if it snows more than 5 inches. We kind of have our assumed then, because our comma and then our pause, then school will be closed. So kind of our conclusion after our comma there. So it did snow 7 inches. So there's our hypothesis. So what conjecture can we make? We can make the conjecture that school will be closed. And what is this following? Is that following law of detachment or law of syllogism? Well, when we go from hypothesis to conclusion and they give us a hypothesis, we can conclude basically the conclusion. That's law of detachment. So law of detachment. All right, we're going to jump to one other concept here that's not in our notes, but it is what is called a biconditional statement. And a biconditional statement, when we have our if hypothesis, then conclusion, and then we have our converse, if the conclusion, then the hypothesis, if I could talk, if both of those are true, then we can actually combine this into a biconditional statement, adding the words if and only if. So hypothesis, if and only if, the conclusion. So it lets us go back and forth, basically make both of these because they're both true. So a lot of times you'll see IFF, if and only if, like that's kind of the in-between, because we got to always have some sort of shortened version there. But definitions are then automatically biconditional statements. So, if and only if are biconditional statements. Let's take a look at one. So here's an example. A lot of times we'll use our arrow symbol too, going kind of both directions, showing P can go to Q, Q can go to P. So a polygon is a triangle. If a polygon's a triangle, then it has exactly 3 sides, and vice versa. We can turn that into a biconditional. A polygon is a triangle if and only if it has 3 sides. So notice there's no if, and then we change the middle to be if and only if, and we just have our hypothesis, if and only if, our conclusion. And again, we can go back and forth writing both the conditional and the converse, and they're both true. So that is biconditional statements.